Okay, I want to say something about this again. You want to know these two here because I promise you they're going to make life easy for you. So just remember, write it down somewhere, beta v over c, gamma 1 over square root 1 minus beta squared, greater than 1. These are just going to really make your life easy. All right, so let's have some more examples with this proper time and dilated time. Remember, dilated time is always greater than proper time. Just think of the eyes, the pupil being dilated. Okay, you are playing baseball near a playful bird which flies past you just as you hit the ball. The bird continues to fly at a constant velocity, reaching an outfielder just as she catches the ball. Which of the following statements is true? So everybody pause your video and figure out the answer. Okay, let's talk about it. So the bird was right. Okay, first of all, what are the events? The first event is when you hit the ball. The second event is when the outfielder caught the ball. So, in which reference frame did both events happen at the same location? Well, remember, the bird was right there when you hit it. The bird was right there when the outfielder caught it. So who measures the proper time? It's certainly not you, right? It's certainly not the outfielder. It's the bird, okay? Because in the bird's reference frame, the bird was at the same location relative to the bird, not relative to the ground, relative to the bird for both events. So you got to be really, you have to understand this. If you don't understand this, you won't be able to solve any relativity problems. So make sure you understand the difference between proper time and dilated time. You have to understand that. So go back and review this if you have to. Okay, let's just do a crazy, Okay, let's do a crazy example. Let's say that we have the technology to make a rocket that has a speed of 0. How many there? 9999999. Yeah, okay? So that means 99.9999 speed times the speed of light, right? Right? Because remember, beta is v over c. So you plug it in the gamma formula, and I promise you, so that would be 1 minus 0.12345 squared, negative 1/2 power. So that's gamma. You get 707. Okay? So what does that mean? So that means, like, let's just say the Velma and the Mort thing. So, Velma, right? Velma just says, 1 second. But if Velma's rocket was going at this incredibly crazy speed, Mort would measure 707 seconds for that light to go like this. It's incredible. Now, it's nice to have an equation, right? Because look, see this graph, this graph is okay, but, beta at 0.999999, right? Well, where's 0.999999 on this graph? I don't know, it's up here somewhere, right? So this graph doesn't help with this particular problem. So that's what I mean. You got to use the equations. Sometimes you have to use the equations because the graph just doesn't make it. All right. Okay, here's another great video clip. It's the light clock video, but they do a really nice job on it. You can actually see it. So again, this is on Canvas. It's under the video module. Light clocks video clip. Make sure you see that video clip. It's really, really good. All right, now, if you're like most people, myself included the first time I heard this, I didn't believe any of it. I thought the physicists were nuts. So don't feel bad if you feel that way. It would be nice to have some experimental evidence of this, right? So let's talk about some experimental evidence of this. Okay, so this is Fermilab, so just who cares? It's just a particle accelerator. Again, missiles and rockets don't travel near the speed of light, so they really can't be used to do real good experiments. But when you accelerate protons or electrons or whatever, they go at nearly the speed of light. So you can use these particle accelerators to do all these awesome relativity experiments. Okay, so here's a muon. Okay, a muon is another subatomic particle. It's just, okay, and it doesn't last very long. It's called an unstable particle. So if you have a whole bunch of muons at rest, the average lifetime will be 2.2 microseconds. So if you have like a billion muons, that means that most of them, they will decay or die after 2.2 microseconds. Okay, so this was an experiment that was done in Mount Washington, New Hampshire, in the late 50s. This experiment was done by, I think, a Harvard guy, an MIT guy, and some other people. Basically, they made a movie to help teach relativity to their physics students. Okay, so here's a mountain, Mount Washington, tall mountain, right? So what they did, okay, so muons come from outer space, you know? So we call them cosmic ray muons. And let's just say they travel at 0.994 C. That's what they do. So nearly the speed of light. And they knew that. People knew that because they detected them, they measured. All right, so here's the experiment. So the physicists, they had a detector at the top of Mount Washington. And they detected 568 muons per hour. Okay? Now, remember, the muons are traveling at nearly the speed of light. And so the muons, so here's Mount Washington. Okay, so the muons, they count 568 muons per hour. Now, the muons are traveling at nearly the speed of light, but they only live, you know, the time, lifetime, average lifetime, is 2.2 microseconds, right? Okay, well, so, you know, so you can figure out how far they'll go before they decay. So, you know, again, distance equals speed times time, right? And so the speed is 0.994 speed of light. The time is 2.2 microseconds. And so you can figure out the distance, you know. Now remember, this was an average. So you're going to have some that are going to live a little bit longer. You're going to have some that live a little bit shorter. But, you know, but anyway, all I'm saying is just by doing the simple calculation, you're going to realize that nearly all of them will have decayed by the time you get to the bottom. So just by doing a simple calculation, they figured out that most, so again, you start with 568, you expect most to decay, so you expect to get 27 muons per hour at sea level. Okay? Pretty simple experiment, right? You know, not a big deal. Okay, so you do the experiment. And this is what they got. So they expected most of them to decay by the time they reached the ground. So they expected 27 per hour. When they actually did the experiment, they detected 412 per hour. Now that's a huge difference, right? I mean, come on. 27 compared to 568 to 27 compared to 568 to 412. What in the world is going on? I mean, that's insane, right? It's insane. Well, relativity answers the question. All right. Yeah, so 412 was much larger than 27. Well, I think, again, what are the two events? The two events are, the first event is the muon being detected here. The second event is the muon being detected there, right? Now, who measures the proper time? Is it the experimenter or the muon? That should be pretty simple, right? The muon was right here when it got detected. The muon was right there when it got detected. But come on, according to the muon, where was the detector? Right next to it, right? I mean, the muon is right here, the detector's right next to it. The muon is right here with the detector right next to it. So the muon was here, event 1, here, event 2. So the muon measures the proper time. The experimenter, come on, who knows where the experimenters are, right? The experimenter, you know, here's event 1, here's event 2. The experimenter is just here sitting on his, you know, sitting on a chair or something like that. All right, so who measures the proper time? The muon. Who measures the dilated time? The experimenter. Okay? So the proper time is measured by the muons. So delta tau is 2.2 microseconds. So what's the dilated time? Well, what do you got to do? What do you always got to do in relativity? You got to figure out beta and gamma. Okay? Because remember, here's the equation. Delta T equals gamma delta tau, right? Okay, so gamma is 1 minus beta squared, negative 1/2. So that's going to be 1 minus 0.994 squared to the negative half power. So I think hopefully I did that. Okay, yeah, I did it, right? Okay, so here's gamma. Gamma is 9.14, right? So this is 9.14 microseconds. So make sure you understand this. I mean, not microseconds, just 9.14. Okay, so delta T is 9.14 times 2.2 microseconds, which is 20.1. Okay, let's just think about this. According to the muon says, I only live 2.2 microseconds. But remember, the muon is moving relative to us, the experimenters. So we say, no. We say, in our reference frame, the muon actually lives 20.1 microseconds. Okay? We say that the muon lives 9 times longer than the muon measures its lifetime. Well, come on. If the muon lives 20.1 microseconds rather than 2.2, it can travel a lot more, it can travel a lot longer, right? Make more distance. So basically, the fact that we say that the muon lives 9 times longer than Isaac Newton would say, for example, explains why more live at the bottom, okay? Because they live longer, so they travel longer, so we expect this. So this is like the Isaac Newton number, no time dilation. This is the special relativity number. Obviously, the special relativity number is correct. Okay, here's another one. So in 1976, they, at CERN, that's in Geneva, Switzerland, they accelerated muons to 0.9994 C. So they really got them going. Then they measured their average lifetime, and it was 30 times longer than the lifetime at rest. 30 times longer. And that exactly agrees with the relativity prediction. Okay, now this is really cool. All right, so sometimes I teach this, and people say, Brother Weber, muons, pions, you can't see these things, give me a break. I don't believe a word of it. How about airplanes? Okay, so the most accurate and precise clocks are what we call atomic clocks. So what they did for this experiment, they had 2 identical atomic clocks. They put one on the ground, they put one on an airplane. The one on the airplane flew around for a while, around the world or whatever, I don't remember, and then it came back. Now, what would Isaac Newton say for the time? The same. What would Einstein say? Different. Well, they were different. But then to make sure, then they switched the clocks, right? And then so the one that the one that flew last time was stationary. Then the one that was stationary, they flew that around the Earth, and then they came back and they checked the times. Different. Okay, so the first time they did it in 1977, they agreed to relativity to within 10%. That's not bad the first time you do an experiment. Then a year later, they improved their experiment. They did the same thing, and again, the times were different, just like relativity said, to within 1%. That's amazing, right? It's amazing. Okay, now here's something else. So we all know about the GPS. The world's economy depends on the GPS, right? The global positioning system. Well, it turns out that if the people who program the GPS, if they did not program into it the relativity equations, the GPS simply wouldn't work. So here's a sentence I want to just read. Okay, if the relativistic effects of time dilation, discussion, blah, 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 okay, forget those, and the gravitational effects of the present chapter, okay, forget about that, were not properly taken into account, the GPS system would fail after only a fraction of an hour. So if you ever use a GPS, you know, like on a bike or if you run or something like that, or you know, like I say, banks, everybody uses GPS. If they didn't use the relativistic time dilation equations and other things, the system would die after minutes. So the fact that the GPS works is evidence that relativity is correct. Okay, I have one last evidence. So I used to work here, so I kind of think it's pretty cool. All right, so let's say you want to do an experiment with muons at Fermilab. Now that's kind of a problem because, see, Fermilab is a proton accelerator. Or you can accelerate antiprotons, but it's not a muon accelerator. So, you know, you can't go to Sears and say, I want some muons. You know, you're going to make them. Okay, so you're going to make your own muons. So this is how you do it at Fermilab. So you have the proton beam, you know, going around and around. And then you extract it, and you smash it into a target, usually like a thin foil or something like that. And so so this is this proton's going nearly the speed of light, smashes into a stationary target, and then pions are created plus other junk, which we don't care about, so we just call it X. This is just other junk we don't care about. Okay, cool. Now, pions are unstable, so the pion, after a short time, will decay to form a muon plus other stuff, plus a neutrino, I don't care, all right? So it's a two-step process. So first you smash the target to get pions, then you wait for the pions decay, and finally get the muons. Two-step process. Okay, now, here's the thing. Pions are unstable. They only live, average, 2.6 times 10 minus 8 seconds. Muons, we already talked about, unstable. Average lifetime, 2.2 times 10 minus 6 seconds. Okay? So this is an experiment. You know, you want to get a beam of muons. So you have to, you got to build a building. You got to put detectors in the right places. And so here, you got to make sure you put your building with the detectors at the right place. So this is what I'm talking about. So you have your proton beam smashing your target, and then the pions are created. Now remember, pions live 2.6 times 10 minus 8 seconds, and then they decay to form the muons. But the muons only live 2.2 times 10 minus 6 seconds. So this is what I'm trying to say. The pions live for a while, right? Not very long, but for a while. So are you going to put your muon detectors here? It'd be pretty stupid, right? Because they're still pions. There's not muons here. So you don't want to build your building here. You can build it anywhere you want here, but you don't want to build it here because by the time they've gone this far, they've decayed into something else. And this is, this is money. I mean, this is like tens of millions of dollars because you got to build a building and you got to build these gigantic complicated detectors, So you really want to make sure you build it at the right place, right? Again, no, yes, no. All right. Now, so all I'm saying, you got to be careful. Now, you got to figure out these distances, right? You got to figure them out to figure out where you're going to put your building. Okay, so you want to know how far this is, right? So you don't build your building here. Okay, so the distance for the pion is speed of the pion times time of pion. Okay, the speed is 0.999. Did I say that somewhere? We're going to say that it's going 99.9% of the speed of light. So the speed is 0.999 speed of light, right? Then the time is this, and you get 7.8 meters. Okay, piece of cake. All right, what does that mean? That means you better not put your building here, but you can put it, you can start building it anywhere after 7.8 meters from the target, right? You can put it 7.9, whatever, You just can't build it any closer than 7.8 meters to the target. That's what it means, okay? Now, if you do that, you're making a very expensive mistake. Why do I say? Okay, so yeah, so what we just said, so the target's right here. You can build your building right there, 7.8. Come on, okay. But this is completely wrong, completely wrong. Because remember, who measures this lifetime? This is for a pion at rest. These pions are not at rest, right? They're moving. So that means that according to us, they're going to live longer than they would at rest. So we can't use this number, this distance. We're going to use the relativity. So delta t equals gamma delta tau, right? So let's see. So delta tau is the proper time, right? The time at rest, lifetime at rest, 2.6 something minus 8. Then we have to do the gamma. Gamma is 1 over square root of 1 minus beta squared. And this comes out to be 22.4 times the lifetime, times the proper time, which is 5.8 times 10 minus 7 seconds. Okay? So this is the proper time. This is the dilated time. It's very much different. So then we calculate the distance that the pion travels. 0.999 times the speed of light times the time, 174 meters. Okay? So, if you didn't use relativity, you'd build your building right here, waste $50 million, because you're only building at 7 point, whatever it was, 8 meters from the target. You've got to build it out here, 174 meters from the target. And if you go to Fermilab, guess what? That's where the building is. It's called the muon building. They're not real creative. All right, so once again, relativity, you got to do it. All right, let's see. All right, let's quit.